Welcome to this course on machine learning using Python programming. In the previous lecture, we have seen gradient descent method and momentum update rule for updating different parameters of machine learning model. And in today's lecture, we will see multiple linear regression. So, as we have already seen, in case of multiple linear regression, there are more than one independent variables. So, we are assuming there is a linear relationship among dependent variable and different independent variables. So, in that case, our model will be y is equal to b naught plus b1 x1 plus b2 x2 up to bn xn, where x1, x2 up to xn are independent variables and y is dependent variable. So, y is depending on x1, x2 and so on, and since there is a linear relationship, so it can be written as y is equal to b naught plus b1 x1 plus b2 x2 and so on. So, in the previous lectures we have seen different notations that we use, and so b naught can be written as theta naught, b1 can be written as theta 1. So, in that case the same expression can be written as y is equal to theta naught plus theta 1 x1 plus theta 2 x2 and so on, but it is representing the linear relationship among y and x1 x2 up to xn. So, it means y is linearly depending on x1 x2 up to xn. So, here as we have xi's in all the expressions, only in the first expression we are not having any xi. So, there is only b naught. So, here we can add one new variable, that is x naught, and this variable value will always be 1. So, we can treat it as by adding a new feature in our data set corresponding to x naught, and its value will always be 1 for all the instances. So, then we can write our model as y is equal to b naught x naught plus b1 x1 plus b2 x2 and so on. So, we can write compactly this expression as y is equal to summation I is equal to 0 to n theta I xi or bi xi. So, this equation is called as the hypothesis function or just hypothesis, and we can represent it as h naught. So, our hypothesis is this, and the need is to find the appropriate values of these coefficients theta naught, theta 1 up to theta n, or that we say that we need to find these models parameter values, and this we do by using the data set. So, we will learn these coefficient values from the data set, and once these values are learned, we can always predict the value of y for the given new instance x. So, we have already seen there are two popular methods, normal method and gradient descent methods that we have seen, but this is the multiple linear regression. So, here we are having more than one independent variables. Now, multiple linear regression can also help us to find out which variables we should include in our model and which we can leave, because in the given data set there may be large number of features, large number of variables, and few of these variables may not contribute in the prediction of dependent variable y. So, we can leave those features, because if we will include those features in our model, your model prediction may not be correct. So, it is always beneficial to leave those features that are not important in predicting the value of y. So, this we will see in today's class how we can find which variables are important and need to keep in our model and which variables we can leave. So, whenever we are building a linear or logistic regression, so of course, we are talking about multiple linear regression because there are more than one variables. So, in that case, variables that are already proven in the literature that these variables are related to the outcome, these variables we can keep in our model. So, first this is the first way to check which variables we need to keep in our model. So, we can find in the literature which variables are related with the response variable or the dependent variable. So, we can keep those variables in our model, or we can check whether the variables that can either be considered the cause of exposure or the outcome or both. So, those variables are also important and we should keep those variables in our model. Then interaction terms of variables that have large main effects, we have to keep those variables also, and we will see some more details on these type of variables. And we should see the variables that have a large number of missing values or low variability. So, these variables are better to leave, because if we are having these variables that are having lot of missing values or there is no or very low variability in that variable, so it can hamper the outcome of the machine learning model or the prediction. So, it is better to leave these type of variables where missing values are large and variability is very low. Then variables that are highly correlated with other predictors, or we can say that if we are having independent variables that are correlated with each other. So, in the previous class we have seen that this is the case where collinearity occurs in case of multiple linear regression. So, we should take care of this, that if variables are independent variables are correlated with each other. So, we need to take care of that also. In that case, we should leave few variables that are correlating with other variables. So, if two variables are correlated with each other, we should keep one and we can leave the other one. Then variables that are not linearly related to the outcome. So, those variables we should also, if we will include those variables in our multiple linear regression case, so our predictions will be wrong, because these your outcome is not linearly related with this variable. So, it is better to take care of that also. So, collinearity we have already seen, it is a situation in which two or more independent variables are correlated or highly correlated with each other. So, it means they share some degree of linear relationships, and in that case if we will take all these variables in our model, your prediction may be wrong. So, why the prediction may be wrong? Because it will make it difficult to determine individual effect of these independent variables on the dependent variable, because these variables are correlated with each other. So, we can't say y is how much variability in y is explained by one particular independent variable if it is related with or it is highly correlated with another independent variable also. So, let us see one example of this. If you are predicting house prices and you are considering two independent variables in your model. First independent variable is number of bedrooms and second independent variable is square footage of the house. So, your price of house is depending on number of bedrooms as well as square footage of the house. So, both of these two independent variables, number of bedrooms and square footage of a house, these two are highly correlated with each other, because the bigger bigger house will definitely have more number of bedrooms, and in this case we can say both of these two independent variables are highly correlated with each other. So, it is better to leave one of these variables, otherwise there will be this collinearity problem in your model, and in that case your predictions may not be correct all the time. We will see the impact of this on the regression model. So, first of all, unstable coefficient estimates. So, if we will have correlated independent variables, then coefficient of these correlated variables may become highly sensitive to change in the model, because if you will change in the coefficient of one variable, one independent variable, so because of that, since other variables are highly correlated with this variable, so it may lead to large variance in the estimated coefficients, and it will be very difficult to see the individual effect of each variable, because these variables are related with each other, and so highly collinearity will make your model less reliable. So, it is always better to reduce the collinearity, to first whether the collinearity is there in your model. If it is, then you try to leave a few independent variables that are highly correlated with other independent variables, and in this case your model will be less generalizable also. So, suppose you are taking all the independent variables where collinearity occurs and you are learning from that data. In that case, whatever model you will learn, when you will predict independent variable value for the new data, in that case you may not get better results or correct results, because of this collinearity problem. So, it may work well on the training data, but may not work well for the testing data. So, if we want to make our model more generalized, we should reduce this collinearity in case of multiple linear regression. Now, we will see how we can detect this multi-collinearity, and then how we can mitigate it. So, there is variance inflation factor VIF. So, using this variance inflation factor, we can find out whether collinearity occurs in our data set or not. So, what is this VIF? VIF is a common method to detect multicollinearity, and you will need to calculate VIF for all the independent variables or for all the predictors in the data set. And it has been seen that a VIF value above 10 is often considered indicative of multi-collinearity or high multicollinearity. So, if VIF value is less than 10, then we can assume there is low multicollinearity, and if the VIF value is very less, so it is close to 1 or 2, then in that case you can assume there is no multicollinearity. But if it is greater than 10, then there is high multicollinearity, and in that case we need to remove some variables that are highly correlated with other variables. So, we can address collinearity by removing one of the correlated variable and combining them into a single variable. So, sometimes we use any dimensionality reduction technique also, like PCA. So, here if more than one variables that are correlated with each other, so we can apply principal component analysis or any dimensionality reduction technique. So, basically if we are using principal component analysis, it may combine these highly correlated features into one feature, and in this way we will be able to have the effect of all features, but only that are incorporated in a single feature. So, if you are finding there is the case of multicollinearity in the given data set, then these are the two options. Either we can apply principal component analysis, and in this way we are trying to combine highly correlated features, or we can remove few features that and leave only one feature where all these features were highly correlated. Or we can apply regularization techniques also. We will see what are regularization techniques in later lectures. So, let us see what is VIF and how we will calculate, and then based on the value of VIF we will decide whether the high collinearity is there or not. So, VIF is a statistical measure that is used to detect the presence and severity of multicollinearity in a regression model that we have just seen. And how VIF is defined. So, as we have seen that VIF we will calculate for all the independent variables. So, we can say that we will we can define VIFJ. So, VIFJ is representing the VIF value for jth independent variable or jth predictor. So, VIFJ is defined as 1 upon 1 minus Rj square. So, what is Rj square? So, this is R square value for the jth variable. So, basically Rj square, what is this Rj square? We will first understand what is R square, then we can understand what is Rj square or any Ri square. So, R square is a metric. This is a metric that is used to evaluate the regression models. So, basically R square gives us how well your model is fitted to the data, or how well the predictions will be from the learned model. So, R square, the definition of R square we will see later when we will study how to evaluate different regression models. So, we will first of all learn all the regression models, and after that we will have one lecture on evaluating these regression models. Then we will see one or two metrics. One of them is R square, another is R adjusted square, and so on. So, but both of these two metrics, R square and R adjusted square, so these are used to evaluate which regression model is better, or if you are by seeing the value of R square you can find out how well your model is fitted to the data. And this R square is called as coefficient of determination. So, we can say that what is now Rj square. So, Rj square is R square obtained by regressing jth independent variable on all other independent variables in the model. So, what we are doing, whatever number of independent variables are there, we are taking jth independent variable as a dependent variable and rest of all the independent variables as the independent variable, and then we will train this model, and then for that model we are calculating R square, that is Rj square, and this we can do for all independent variables. In this way we can find out R1 square, R2 square up to Rn square if there are n number of independent variables, because in that case by seeing the value of R1 square or R2 square or in general any Rj square, we can find out how much jth independent variable is depending on rest of the independent variables. So, if it is depending on rest of the independent variables, it means these are highly correlated. So, we can now calculate VIF j is equal to 1 upon 1 minus Rj square. So, here we are treating there are only 3 independent variables, and we will made in this case 3 models. So, first we will regress x1 on other remaining independent variables, then x2 on remaining independent variables, then x3 on remaining independent variables. So, we will have 3 different models. X1 is equal to b naught plus b1 x2 plus b2 x3, then x2 is equal to b naught plus b1 x1 plus b2 x3 and so on. And then we, for all these 3 regression models, we will calculate R1 square, R2 square and R3 square, and R1 square will represent the proportion of variance in x1 that can be explained by x2 and x3, and in the same way R2 square will represent the proportion of variance in x2 that can be explained by variable x1 and x3 and so on. So, basically this R1 square will give you how much x1 is depending on x2 and x3. R2 square will give you how much x2 is depending on x1 and x3. Similarly, R3 square will give you how much x3 is depending on x1 and x2. So, when we will put these values in 1 upon 1 minus Rj square, we can say that VIF value will be 1. In that case, the independent variable is not correlated with any other variables, and there in this case there is no multicollinearity. Why? Because when Rj square for all j will be 0, it means, for example, if R1 square is 0, it means there is no relationship between x1 and x2 x3. So, x1 is not depending on x2 and x3, and that is why R1 square is 0. So, in the same way, if there is no independent variable that is depending on other independent variables, in that case all these Rj squares will be 0, and in that case your VIF j for all variables will be 1, and then we will say that all these independent variables are independent to each other, or there is no correlation between these variables. So, if VIF is 1, so you will say that for any independent variable, if VIF is 1, the independent variable is not correlated with any other variable, and this is the case of no multicollinearity. If VIF value is between 1 and 5, then we say there is a moderate correlation, and it is not severe enough to be problematic. So, we can ignore this, and we can now, in this case, we can take all the independent variables. But if VIF is greater than 5, in that case it indicates high correlation, and there may be problem because of this multicollinearity. So, we need to take care of this, and if VIF is greater than 10, in that case it indicates serious multicollinearity, and we must choose some way to reduce this multicollinearity problem in our data set. The second problem that we may have in case of multiple linear regression, that is confounding variables. So, what are these confounding variables? Let us understand. Confounding occurs when relationship between independent variable, that is called as predictor, and dependent variable, that is called as outcome or response variable, is distorted by presence of any other variable. So, it means we have one or more independent variables. So, we are talking about when we are seeing relationship between one independent variable and dependent variable. So, the relationship between these two is distorted by another variable, and that variable is called as a confounder variable. So, if this is the case, and we are not considering this confounding variable. We are not in our data set, we are only having these independent and dependent variable, while there are some confounding variables that are distorting these relationship between independent and dependent variable, then there may be problem and your prediction results may not be correct. So, we need to find out whether there are some confounding variables, and then we need to take care of that. So, we can say that a confounder is a variable that is associated with both independent variable as well as dependent variable, and it leads to a misleading interpretation of effect of independent variable, because we are assuming dependent variable is only depending on this independent variable, but there is some other variable that is distorting relationship between this independent variable and dependent variable. So, we must need to take care of, we must include that confounding variable also in our model. So, let us see one example. Suppose we want to see the effect of exercise on weight loss. So, weight loss is the dependent variable and exercise is the independent variable. So, we are assuming your weight loss is directly related to the exercise, and but if we actually see there is another variable, that is calorie intake, and we should take into account this calorie intake variable also, because if we are not taking calorie intake, in that case we will not be able to say what is the actual effect of exercise on weight, because exercise as well as calorie intake, both of these two variables we need to keep in our model, then only we can get the effect of exercise on weight loss, because if calorie intake is low and same amount of exercise is done, then weight loss may be different. If calorie intake is high and same amount of exercise is done, then weight loss may be value may be different. So, we can say here that calorie intake is the confounding variable in this case between exercise and weight loss variable. So, if we will not consider calorie intake, in that case there may be problem. So, what we can do? So, what we will do, we can now do two things. We can divide the data set in two parts. In one part we are having those instances where in this particular example where calorie intake is low, and the second part of the data set where calorie intake is high, and then we will create our model for both of these two different parts of the data sets, and then we will check whether the results are consistent among these or not. So, if these are consistent, it means calorie intake is not working as a confounding variable, but if results are different, in that case this is important variable and this is the confounding variable that we need to include in our model. So, this is called as the technique of stratification. So, in this case we analyze these groups separately. So, one group of this high calorie intake and one group of low calorie intake, and then we will make our model for both of these two groups, and then we will check whether the results are consistent or not. So, in this lecture we have seen multiple linear correlation, multiple linear regression, and in case of multiple linear regression we must check these two problems or assumptions, you can say, if there is multicollinearity as well as if they are confounding variables. So, we need to take care of these, and then in the next lecture we will see the remaining topics of multiple linear regression. So, I am stopping here. Thank you.